What I have this morning is a PowerPoint presentation, and then I've hooked up another computer that has our ventilator simulator on it so that we can switch screens and actually walk through the inside of the ventilator. Okay, so let's talk about ventilators in general. And by the way, I can send you these slides so you don't have to take vociferous notes. And then I believe this video will also be, well, it is being recorded. So please don't curse me out. And or actually, you can. It'll probably be a great thing. My kids would like it. And what we'll do is we'll have this video available for you to look at as well. Medical indication for mechanical ventilation. There are really three reasons why we put people on mechanical ventilators. The first is oxygenation. We want to increase their arterial oxygen, and we're unable to do it with what is described as low flow and high flow respiratory devices. These are masks, cannulas, and more devices, disposable devices that can take higher flow rates and higher oxygen concentrations. So getting very granular here, when we walk around, the oxygen level that we're breathing in is 21%. And what that does is it allows our body to transfer oxygen across our alveolar capillary membranes and achieve an arterial oxygenation of around 105, 100 to 105. And so part of the purpose of respiration or ventilation in general is to take oxygen in. When people present with a deficit, then we need to supplement their oxygen, and we generally initially will put them on a cannula or a mask, and we'll increase that oxygen concentration from room air, which is 21%, all the way up to, now with these smaller devices and these low flow devices, we can get about 50% oxygen. So what is that? It's 50% oxygen and the rest is nitrogen. There's, in the atmosphere, there's very little CO2. And of course, we add to it. So when we are no longer able to manage people with our external devices, then we commit people to mechanical ventilation. We can do it non-invasively by putting a mask on their face, or we can do it by putting an endotracheal tube or a tracheostomy tube into the patient, and then connecting them to the ventilator. So that's oxygenation. That's one reason why we put people on ventilators. The other reason we put people on ventilators is to remove CO2. The word ventilate itself means to aerate or to move air. And when we talk about how the body responds, ventilation really is about CO2 removal. So we ventilate patients to remove CO2. And, normally we walk around with our CO2s, our arterial CO2s, after we've removed our excess CO2 in the 40s. And when I'm saying in the 105s and in the 40s, I'm talking about millimeters of mercury. And we're talking about what you may have heard of as blood gases. These are the values that are in blood gases. So we walk around hoping to send our arterial blood out to our organs again and to have that level of CO2 of 40. As patients tend to fail in ventilation, these patients fall into the category of respiratory disease. And a good example of this would be a COPD patient, a chronic obstructive pulmonary disease patient. So the ventilator is applied, and it basically, using positive pressure, drives a ventilatory flow through the lungs and helps wash out CO2. And then the third function of the ventilator is to take over the work of breathing. So when we're walking around here, we don't think much about breathing. We don't think about our work of breathing. We may think more about breathing when we start to exercise. We can't catch our breath. And that is because we have a high CO2 level, and we have motion, and the body senses work. So the third reason to put somebody on a ventilator is to alleviate that work. Sometimes we alleviate that work intentionally by anesthetizing and paralyzing patients during an operation. And that's another reason where the ventilator needs to take over the work of breathing. So there's three reasons to put a person on a ventilator: to improve their oxygenation, to ventilate them and remove their CO2, and to take over or alleviate the work to breathe. So let's talk about ventilators. There are many ventilators out there, but not all ventilators are created equal. There are huge differences in the quality of mechanical ventilators. So what is the importance of a mechanical, or what are the functions of a mechanical ventilator? As we talked about in the previous slide, it has a therapeutic function. Remember, it's going to supplement oxygen. It's going to help drive up oxygenation, manage oxygenation. It's going to remove CO2, and it's going to take over the work of breathing. In order to do that, in order to do that effectively, an ICU ventilator has to have three major functions. It has to be that therapeutic device I just referred to. It has to also provide monitoring, and it has to provide diagnostics. So a ventilator really is a platform at the bedside that's providing therapeutics, diagnostics, and monitoring. And a lot of people don't realize that. Within the ventilator, what allows us to achieve the therapeutics is the engine of the ventilator. And the engine of the ventilator generally fall into three categories. You have a proportional solenoid, you have a blower, and you have pistons. Those are the three types of engines you'll run across. When I say engine, it is the thing that's generating the force to inflate the patient's lungs. When I say PSOL, I'm talking about a set of solenoids, a set of valves that open to a particular level and allow oxygen and air to be mixed and then to be delivered into the ventilator circuit and to the patient. And we'll look at a picture of we'll look at a terrible drawing by me of what a ventilator and circuit and patient might look like. Proportional solenoids are very fast in terms of responding to the patient, and they're very precise. They're considered the highest end of mechanical ventilation. They're considered the creme de la creme of mechanical ventilators, if such a thing can be. And of course, when you look at the price point of ventilators, the ones that you hear, another fallacy that we've heard in the pandemic is that ventilators cost $50,000. Well, I guess that's only if somebody is a sucker, because ventilators do not cost $50,000. In general, the average selling price of a high-end, fully featured, PSOL-based ventilator is around $30,000. So I've never heard of a ventilator costing $50,000. Just not true. So the high end of ventilators are proportional solenoids, and they run at about $30,000 a piece, and they're typically seen in the ICU. Then the next type of ventilator engine employed is a blower, a fan, or a turbine. They essentially are a fan or a turbine like engine, similar to what you would see in an airplane. And they generate force. They do so without requiring high pressure lines. So let me back up. That I was talking about the greatness of proportional solenoid ventilators. I'm a fan of P-sol ventilators. But one of the downsides of P-sol ventilators is you have to plug in, you have to take the oxygen and plug it into the wall. You have to take the air and plug it into the wall. And so the downside is when it comes time to transport that patient back to the operating room or to transport that patient to radiology, to CAT scan, to those sorts of areas, it becomes difficult. You need to then have a set of tanks, and you have, or a oxygen tank, and the ventilator itself has to come with something called a compressor. Now, our ventilators are built with compressors inside, so it's a great option. It's a great feature, I should say, not an option, for our proportional solenoid ventilators. And one of the downsides for the care staff is that they have to source all of these things, the gases, in order to move the patient to somewhere like the operating room or radiology. A blower does not. A blower serves as that force. A blower will actually generate the required air, and what you're left looking for is an oxygen tank. And most of the time, a simple E cylinder is sufficient. It can be plugged right in, and you're able to move and provide oxygen and air and all the things that are important. So an advantage of a blower-based ventilator is that it has its own ability to generate force. It doesn't require a high pressure line, and you can a tremendous advantage, and where it's become popular is that blower ventilators have found their way initially into transport. They originally came from obstructive sleep apnea and CPAP. That's where we first started using blowers, but blower technology has improved over the last 10 years, and mechanical ventilators are now employing blowers as their source of air. So that's a blower-based ventilator. Many blower-based ventilators are in the mid-range of pricing. So we said 30,000 for the high end. I'm going to say 22,000 for the blower-based units, somewhere in that neighborhood. And again, the pricing strategy is something we can go over in a later call, but essentially companies give you the platform. It's like an automobile. They'll give you the car, but the features you choose can drive that sticker price up. That's classically the way the ventilator industry operates, and it's very similar to the car industry from that standpoint. And then the final engine is a piston. You might remember Christopher Reeve's Superman on a ventilator. Mm-hmm. He was on a piston-based ventilator. Pistons originally came into play because they were very reliable. They could be sent home. They were driven electronically. All you really needed was a power source, and this piston would generate air, a stroke volume, and you could send a patient home. Many paralyzed patients who cannot breathe or need support breathing are on piston-based ventilators. That's what you typically see under the wheelchair. There was one piston-based ventilator that was famous in the ICU. It was this giant device out of University of Winnipeg. a Dr. Magda Jonas, created something called the Winnipeg Jet, the Winnipeg ventilator. And the Winnipeg ventilator was a wonderful piston-based ventilator that eventually Puritan Bennett took on and grew it into an ICU-capable ventilator. It was called the 740 and the 760 ventilator. But in general, the problem with pistons is they have a stroke volume. So for a paralyzed person, it's fine because he's not triggering his own breathing. But for someone who is breathing on their own, the stroke volume can be a problem because you can be at one end of the breath and you're at the end of the piston, it has no more, and you want more air, and you have to wait for it to move back, reset itself, and start that stroke again. So pistons have been very reliable ventilators for the home, not so much for the intensive care unit. So those are the three types of ventilators, engines that you'll run across. This is a typical layout. So I picked a happy face here, but essentially what we have again are these sources of gas. You can have metered air, a blower or a piston replacing that air source out of the wall. And then you have oxygen, and oxygen will come from the wall or a tank or even a concentrator. And we can talk about the concentrator later, but a concentrator is a low level, I shouldn't say low level, a low oxygen producing device. It doesn't produce high levels of oxygen. Yeah, that was a tongue twister. Okay, so they plug into the back of a ventilator, and I have a video I'm going to send to you guys to look at. It's me starting one of our ventilators, kind of doing a walk through the ventilator, basics of the ventilator, and I will, I'll send you that link, and it's also a good video to watch. And by watching those videos, I think you'll have a lot of questions for me next time. So we plug our sources of gas into the ventilator, we turn it on, and the ventilator is going to deliver gas to the patient. It uses two methods. Either it's targeting a pressure level, a pressure above ambient air to drive oxygen in, or it is trying to reach a flow rate. The valve sets itself at a fixed level and lets a constant flow go into the ventilator circuit. And we'll just leave it at that for right now. So the physician chooses, or the therapist chooses, what type of method he wants to ventilate the patient with, and lets the valves go to work. The gas goes in the inspiratory circuit. On the way to the patient, it flows through a humidifier. And we'll talk about humidifiers in a minute, but there are sources of humidifiers that are quite nice. The humidifier, as the name says, adds humidity to the gas. Gas coming in here is dry, and without increasing the temperature and humidity of the gas, the patient who has their normal physiology bypassed will tend to have drying of the lung, drying of their secretions. In the worst case scenarios, casting, meaning fluid drying up and blocking the airway, creating obstructions. So this little guy, this humidifier, is very, very important. And to keep the air warm, we employ heated wire circuits. The circuits, if you look inside them, have heating elements, like a heating blanket would. It basically warms the air, keeps the humidity up, and then delivers to the patient. The patient has something called an endotracheal tube if we're in the short-term window. And if a patient's on the ventilator for longer than 48 hours, then we generally start to consider tracheostomy, which is basically the placement of the tube through the trachea and alleviating the person of having the tube through their mouth into their trachea. Allows a lot of additional function when you put a trach on a patient. A lot of the function that we take away when we put a tube down. So that is a general layout of what's happening with a patient.
Steve, I have a question.
Sure.
Now, a ventilator is a short-term breathing support system not to be on for more than a few days, a week.
So in general, if we look at statistically at mechanical ventilation, most ventilators are removed, the patient's off the ventilator within 24 to 48 hours.
Okay.
And that's because most people who are ventilated are patients that come to us either through trauma or through an elective surgery. And, maybe an emergent elective surgery or emergency surgery, a cardiac surgery as an example. But most patients come to us from the operating room. A smaller percentage, I would put that percentage at around, I would say less than 10%. Last time I looked at the statistics in ventilation application, it was less than 10% for respiratory problems, for true breathing problems, COPD, asthma, things like that. And when I talk about COPD, we're also including in that things like chronic bronchitis and emphysema. And those have two different physiologic drivers. But those patients, in general, they can be on a ventilator. They'll be fine. They'll be found more so in the medical intensive care units versus the surgical intensive care units. And they can be on ventilators for weeks. In general, we try to get patients off, the average of those patients would be around 2 weeks. But there are patients on, for months in the hospital. If the patient is stable, then we begin to move them out of the intensive care unit to the tertiary floors. Some of them have ventilator monitoring floors with a lower nurse to patient ratio. And then eventually they're pushed out to the to a ventilator hospital. There are ventilator hospitals that care for long-term patients on ventilators, and their expertise is in the area of weaning patients, at some point getting the patient off the ventilator. There are tons of them out there. Kindred is one of the more famous ones. Kindred originally was started in Louisville, and their original name escapes me, but I'll think of it in a minute. So those patients that represent under 10% of the consumption of mechanical ventilation actually represent almost 80% of the resources when it comes to the resources allocated to caring for patients on mechanical ventilators. I'm not sure if that's clear, but a majority of patients, from a number standpoint, go on a ventilator, get off in 48 hours. That's the lion's share. That's 90% of the patients that we see. So there's a high flow through that realm. But then there's the 10% that consume, 80% of the resources of mechanical ventilated patient requirements. And those are generally COPD patients, asthma patients, pediatric patients with respiratory diseases. And just as a point of reference, in talking to a lot of the doctors, we're seeing that the COVID-19 patients, they get put on a ventilator. We're trying to manage them with high flow devices, those cannulas and those oxygen devices. When they're actually committed to a ventilator, they seem to be on for a period of about 1 week. That's what we're hearing. And then the weaning process begins, and the weaning is a little bit slower with these COVID patients. There's this exhaustion that is unlike things that we've seen before. And it takes a little bit longer to get these patients off the ventilator. But in general, they're kept under 2 weeks. And in general, the mean is about 1 week. So again, how do ventilators work? They simply put either a pressure level into that inspiratory circuit, or they try to drive a volume, a square flow through that inspiratory. And then they have timing. They open and close the valves to create these breaths. You know, they'll close the expiratory valve and open the inspiratory valve, and gas goes into the circuit. Then they'll close the inspiratory valve and open the expiratory valve, and gas goes out of the circuit. And that's the inspiration of breathing and the exhalation of breathing. And we'll look at this in a second. Vents are very, very smart. You know, they're as I mentioned before, you don't realize that's a platform doing diagnostics, therapeutics, and monitoring at the bedside, but it does. And one of the things it's able to do is it recognizes when a patient is asking for a breath. And it does that by either looking inside the circuit and seeing that the pressure has dropped. So the only person attached is the patient. They must be pulling and wanting a breath to be delivered. Or they look and see, hey, the flow that I put into my circuit didn't come back. There's only one guy here who's taking that. It's the patient. They must want a breath. So it recognizes the person's demand of breathing by either looking for pressure drops or seeing that flow was consumed from the circuit, airflow. And it's really that simple. So some of the critical components that you find in the ventilator are valves, turbines, pistons. We use pressure transducers to measure the flow so we can calculate the volumes. Those come in either hot wire or hot film, and we can talk about that later. And then the valves, exhalation valves, solenoids, magnetic valves, mushroom valves. We have to have valves to exhaust the ventilation, allow the patient to exhale. I keep trying, but. And then I mentioned earlier, what are some continuous revenue streams that you might see by selling a ventilator to a group? You may include a humidifier, and what comes with that humidifier are ventilator circuits, and what everybody wants, especially now, are filters. Do you have any filters for, keep the COVID out of the room? And so those are the continuous revenue streams that you might see. The humidifier is a durable product, but it eats ventilator chambers and circuits. So this is an area where if you sell a large set of ventilators, you can put a hook in to have a revenue stream, a continuous revenue stream.
Steve, is a ventilator circuit, is that just the tubing in and out? Is that what or is that something else?
No, it is. It's exactly what you just said. It's that tubing in and out. There's also a chamber that's, for lack of a better word, the coffee pot, a little hot pot that heats the water, and the air flows through like a Passover humidifier, like the humidifiers that you would, funny enough, use maybe for your child if he's got a little bit of bronchiolitis. And in this case, the gas is directly driven over that heated water, and it picks up humidity and goes to the patient. So I want to kind of summarize on what are the characteristics of high-end, high-quality ventilators. They have this ability to use flow triggering to recognize the flow. They have the ability to set high levels of PEEP and maintain those levels of PEEP. Patients can breathe spontaneously. They're allowed to breathe on their own, and the ventilator just sits and kind of supports them. Generally, there's an active exhalation valve, a valve that is being driven, and the inspiration and the evolution have that. And then these are the modes that I look at on a ventilator to tell me if it's a quality ventilator. Does it have pressure-based breaths, pressure-controlled ventilation? Does it have a SPAP, which is also in other ventilators called BiPAP and bi-level? And does it have auto mode? Auto mode is a smart methodology that kind of lets you tell the ventilator to take care of the patient. And it does a lot of assessment and tells you when the patient's ready to be tried on spontaneous breathing trials and take tube out, things like that. So these are some of the characteristics on high-end mechanical ventilators.
Steve, can I go back to point number 2? What is PEEP?
Thank you. I missed that acronym.
Yeah, I'm sorry. And by the way, we are acronym hell, and I'm sure radiology is as well. And PEEP is the level of positive expiratory pressure that remains in the circuit. Positive end expiratory pressure is the actual acronym. And what it means is we don't let all the gas out of the ventilator circuit. Why? Because we want to keep that lung inflated. And in order to do that, PEEP, not letting them fully empty their lungs, is essentially created by having that valve shut before the patient reaches ambient pressure. So that is, PEEP is the level above ambient pressure that the circuit is maintained at. So if a circuit becomes disconnected, you'll have gas kind of flowing in the room, and that's coming from the PEEP, from the fact that we keep the circuit above ambient pressure.
Does that imply that they exhale less than they would if they were breathing on their own?
No, people adjust. What ends up, as an excellent question, what people do is that they adjust their inspiratory capacity. So we have a inspiratory reserve when we walk around. It's what gives us the ability to walk upstairs or to do exercise or to carry a load. And normally when we're breathing in a middle sweet spot. And then when we have stress, we will increase the size of our volume and we'll go into the inspiratory reserve area. That's kind of a headroom, if you will. We'll start using that headroom. What happens with PEEP is when we apply PEEP, they just shift. They basically shift up into that inspiratory reserve volume, and they still exhale. But it's an excellent, insightful question, because PEEP can cause a person not to be able to fully exhale when used in a manner that there's a therapeutic approach of excessive PEEP to eliminate the patient from fully exhaling and to keep the lung completely inflated at a high oxygen level. Also, when we set our rates on our ventilators too high, we don't give that patient enough time to exhale. So what ends up being the indicator that we have messed up is that we see something called auto-PEEP. Auto-PEEP is unintended PEEP, unintended pressure. So that's a very insightful question. That's a second-year student question. So
Wow,
well done.
way ahead.
Right, it was positive expiratory, what were the other?
Yeah, it's positive end expiratory pressure. It's the pressure right before you take your breath in. Positive end expiratory pressure.
Is that the same as tidal volume?
No, tidal volume is the actual volume that's moved into and out of the lung. And tidal volume is basically the volume. What we do is we deliver a volume to a patient, and our tidal volumes are generally around 500 milliliters. A healthy adult, 70 kilogram, kind of a normal person, and that's kind of the. So tidal volume is the gas that's moved in, and I'll send you a picture of volumes and pressures. It's important to kind of look at that, give you a sense of the physiology of breathing. Let me see. So when we look at the screen of a ventilator, we see that it is increasing pressure and decreasing pressure. So here on the screen, you see basically airway pressure pushing gas in and letting gas out. As it goes up that curve, the air is going in. As it goes up the curve, air in, air out, air in, air out. So, you know, in the old days, we had these bellows that would move up and down and up and down. Now we have waveform screens, okay? And the time it takes between breaths is called the cycle time, and that's really our respiratory rate. So you and I breathe at a cycle of 5 seconds generally when we're sitting at rest. At a rate of 12, when we start to get up and walk around, our breathing changes to a rate of 16. We shorten the cycle time and we increase the volume of our breathing. And that's what happens when we're generally breathing. Again, we look at the pressure. This is the PEEP level, the PEEP of 5. See how it's not at 0? And as the breath goes in, the pressure increases. There's a law, a physics law called Boyle's law. And Boyle says basically as you change the volume of a closed system, you must therefore see a change in the pressure. It's called Boyle's law. So as a person is mechanically ventilated, we increase the pressure or the flow, air goes in, and we see the pressure in the lung goes up and then goes down. Okay? And different sorts of modes of ventilation exist, but this is an example of a pressure-based breath. Then that was pressure. We also are very interested in the flow that's going in, because flow over time is volume. So there was a question about tidal volume. This area here under the curve is the tidal volume that we're giving to the patient. It's the amount of flow. Think of it as watering. I like to use the analogy of watering in the lawn or watering your plants. The higher you turn up the faucet, the more flow you're having come out of your hose. Well, we do the same thing, but we don't have a faucet. We have these valves, these solenoid valves. And as we increase that, valves opening, we see a higher rate of flow. As the lung gets filled up, the flow tends to stop. So if you were to clamp, you would take your hose and pinch it off, it would stop. It would essentially have the flow stop. And that's the exhalation valve in some ways. So that's, we look at peak flows and we look at baseline flows. We look at the pattern that the flow has. A square flow means you're in volume ventilation. A decelerated flow, like we had earlier, means you're in pressure ventilation. And I'm getting way, you know, I'm getting at the eye stage. But generally speaking, these waveforms allow a patient or allow a physician or a nurse or a therapist to look at the ventilator and to do a momentary diagnostic. They can look at that pattern and say, the patient's breathing well, or the patient's not breathing, the ventilator is doing the work. Or, you know, this patient seems dysynchronous. This patient seems like they want to either come off the ventilator, or we better get the therapist over here to tune this ventilator again for the patient. And we have these things called loops. Loops basically take pressure and volume, and they basically create a loop. See if I can get one of these loops to work. Okay. So these loops aren't loops in a minute. But basically, these loops tell us about the work of breathing. The work of breathing is important because remember I said that's one of those three things that we're doing with the ventilator. We're oxygenating, we're removing CO2, and we're taking on the work of the ventilator. So I'm going to stop here, and I am going to see if there's any questions. Okay, let me kind of show you a typical brochure of our product. So there's our product. This is the inspiration. We have two products, the two product lines, the inspiration and the evolution. This is the inspiration. It's a proportional solenoid ventilator. And then the evolution is a blower-based ventilator. And basically, this is a young girl being ventilated. Let's see if I can move this screen out of the way a little bit. And
Yeah, just call them.
the patient has an endotracheal tube in place. They have a sensor at the airway. It's to measure CO2. That's an option we have. And then the ventilator is operating with a set of parameters across the top and a knob. And this is a classic brochure of ours with all our taglines and some of our key features. A couple of simulated therapists treating the patient. And then these are some of the highlighted features, the modes that are very important that people want to see if your ventilator has. We mentioned these earlier, things like SPAP. And I'll give you guys the information to study that. We talked about auto control as an important mode that you see only on high-end ventilators. And there's those waveforms again. And happy family. The patient survived. And we'll talk more about some of these feature sets. I think when we get into competition, be a nice place to talk about some of these things that you see. One of the other very important features that all of our ventilators have, that is a feature no one else has, is something called CliniNet. Every single ventilator has a web server built into it. And that web server takes all of that information from the ventilator and allows you to send it to a screen somewhere on the internet so that a physician using his phone can check out his patient in bed 9, his difficult patient, or a patient who is isolated because of COVID can be monitored without the patient, without the caregivers having to put the downing, down all the PEPs and go into the room to see the ventilator. So this is a very powerful feature and it's unique to us. We have the IP for this, and internationally it's an okay feature. In the US, it's a knockout feature. The ability to see your ventilator remotely is really important. So let me kind of see if I can get out of this, and let me see if I can ask my other computer to share. I will ask the simulator to share his screen. Okay, share screen. Okay, here we are. So this is a simulator. This is a ventilator simulator. This is what our system looks like. And basically the ventilator starts up You choose the type of patient you want. It can be adult, pediatric, and I didn't activate infant on this, but we have 3 types of patients: adult, pediatric. You choose the body weight, how much the person weighs in kilograms. This is kind of allowing you to quick start your ventilator. So you say 70, you accept that. It wants to know the gender. And then it asks you, what type of humidification are you using? In the short term, you asked the question, Ken, about those short-term ventilator patients. Those short-term patients are only on what's called HME. Those are filters that retain humidity. It's after 24 to 48 hours that we start to worry about the patient and want them to have humidity.
Okay.
Anyways, you choose the type of humidity, you hit accept, and you choose your mode. And here are the mode types. You have CMV, SIMV, spontaneous breathing. You have the auto control, but we'll just use CMV right now, and we'll use pressure ventilation, and we'll say go. And the ventilator starts. And basically what you have here in our user interface is you have your monitoring techniques across the top, you have your waveforms in the middle, and you have your important settings along the bottom. That is very, that's a user interface that people really love. It's a user interface that's favorable to clinicians. And the neat thing here is they can actually touch this part of the screen. If they say, hey, I don't want to have peak pressure, my other ventilator shows me tidal volume, then you can put that up there. So they can configure what they want to watch according to their hospital protocol, or according to the disease state, or according to what Dr. Joe, the mean Dr. Joe wants. So it's very flexible. You can look at one waveform, you go 3, 1, 2, 3. There's a place where we trend data. There's also numeric data. So the system is quite flexible. It can look quite simple, or it could get really crazy. And that's really what makes it a high-end ventilator. The patient or the user, clinician, touches a button and drives up how much oxygen they want to give, and bang, bang. So that's kind of a simulation of the ventilator. I don't want to overstay my welcome. I know that it's 8:05, or